All right, so let's pick up with where we left off last time. We introduced this new chapter called aromaticity, and we spent a bunch of time talking about benzene and these benzene derivatives here. And really most of last class was just spent kind of introducing the chapter and then going over the nomenclature of these benzene derivatives. All right? Today we'll get to the actual heart of the chapter, that aromaticity business. But we're going to do one thing first. I'm going to take this opportunity to introduce a new functional group to y'all, what's called a nitro group. This is this strong electron withdrawing functional group. All right, so you'll see it often abbreviated as just NO2. Again, this right here is what we would call a nitro group. All right. But let's kind of expand this a little bit and draw the full Lewis structure of this nitro group here. Okay, we have the nitrogen in the middle, and it's bound to those two oxygens. Let's take this real quick and fill in our missing lone pairs and formal charges. All right, my double bonded oxygen down here needs how many lone pairs? Two, meaning it has a formal charge of 0. What about my single bonded oxygen? I need 3 lone pairs, which means it has a formal charge of -1. And then let's look carefully at our nitrogen in the middle here. It's got 4 bonds, so it's not going to have any lone pairs, but what would the formal charge be? Positive. All right, so we got a lot of formal charge in this functional group here. Remember, atoms don't really like to have formal charges, but there's a reason that we can get away with it here. This negative charge on this oxygen, why is that? How is it stabilized in this molecule here? All right, so I can't, if I was being really good, I shouldn't represent this with just one structure. I should also include its other resonance contributor here. So this oxygen's negative charge is being stabilized through resonance. It can get passed to the other oxygen. All right, so if I was being good, I would represent my nitro group with both of these resonance structures here, showing that negative charge being stabilized through resonance. Cool. All right, so we represent our nitro group. You'll see it just written NO2. On your homework, I had to draw out the full structures, so you'll see these Lewis structures of that nitro group. You'll have to draw them out, but both of these are sort of just, if we're being good, both of them are really our representation of our nitro group, that NO2 group. Okay? And again, we called this an electron withdrawing group. All right, so let's show this electron withdrawing nature of this group. We talked about electron withdrawing groups with regard to our dienophiles in our Diels-Alder reactions. So we said that these electron withdrawing groups, they make these dienophiles even better at accepting electrons because they pull that electron density away from that pi bond. These nitro groups are really good electron withdrawing groups because of the positive charge on that nitrogen. Okay, but I can't stop there with that one arrow, or I'm breaking some rules here. What would be wrong with me just stopping with this one arrow here? 5 bonds on that nitrogen, right? So now I've broken nitrogen's octet here by stopping there. So I got to do one more jump, kicking that pair of electrons onto that oxygen. All right, so this nitro group is good at accepting pairs of electrons because we can pull that electron density onto that nitrogen without breaking its octet, because that will go onto that oxygen. All right, so everybody's going to take a second and draw me the other resonance structure following those electron pushing arrows. What would be my other resonance structure here, showing this electron withdrawing nature of our nitro group? All right, so help me out here. This arrow here represents what? Bond breaking, bond formation, or both? Bond breaking. So this would be bond breaking. So that means that pair of electrons is going from being a bonding pair to a lone pair on that oxygen. And what about this one here? Bond breaking, bond formation, or both? So this is both. Yeah, that pair of electrons is swinging around, forming a new carbon-nitrogen pi bond. All right, my nitrogen has this positive charge because it's got its 4 bonds. Okay, and what else am I missing from that structure on the right-hand side here? Let's look carefully at our conservation of net charge. What's the net charge on the left-hand side? Yeah, all right, so my net charge on my right-hand side here is neutral. Whoops, left-hand side is neutral. On the right-hand side, currently, my net charge is -1, so I'm missing a positive charge in there, all right? And yes, this pair of electrons, or rather this carbon, with its 2 implied hydrogens, was all happy over here on the left-hand side, and then I stole that pair of electrons from it. It still only has 2 hydrogens, so now it's got 3 bonds and no lone pairs, or that carbocation, all right? Just to kind of stress, as I said, managing charges is kind of the hardest part of doing your mechanisms, and carbocations in particular are hardest to spy because of these implied hydrogens, right? So we want to convince ourselves here that this carbon had that complete octet on the left, and when that pair of electrons was taken away from it, it was left with an incomplete octet, or is a carbocation. All right, and then lastly, with these nitro groups, how do we do nomenclature with nitro? Okay, those nitro groups are substituents in the world of nomenclature. They are nitro substituents. So by substituent, I mean they go out front of the name, not in the back half of the name. All right, so if we had a molecule like this, I'm going to just abbreviate that nitro group NO2. I'm going to find my parent chain, my 5 carbons. I'm going to find and name my substituents. Again, this nitro group is a substituent. I'm going to number my ring and then put it all together. So this would be 2-nitropentane. All right, again, that nitro group is considered a substituent in the world of nomenclature. All All right, and so since we've been talking about benzene and benzene derivatives, everybody's going to take a second and name this molecule for me. What do we get?
Nitrobenzene.
Nitrobenzene is actually a pretty cool one. All right, because this is just a nitro group on my benzene parent chain here. Since it's just this one substituent, we're not going to bother putting any numbers into our name. So this is just nitrobenzene. Cool. All right, we'll talk a lot. We'll see this functional group coming up over and over again in these next two chapters. All right. Now we're going to move on to kind of the heart of the chapter, what's called aromaticity. All right, so in order to be classified as an aromatic compounds, all right, we're going to call these our rules of aromaticity. Okay, so compounds are classified as being aromatic as long as they have these two structural features, all right? And we'll talk a little bit more about what it means to be aromatic here in a second, but we're going to work out first on recognizing compounds that are aromatic. They have to have these two important features, all right? So first of all, we're going to use benzene as an example. As you might have guessed, benzene, being the star of this chapter, is indeed considered an aromatic molecule. All right, and that's because it's got these two important features. Number one, it has a fully conjugated ring. All right, so we introduced this idea of conjugation last chapter, right? When we have that perfect spacing of our double bonds, then these p orbitals containing these pi electrons, right? These pi electrons are being shared for these double bonds, but when they're lined up in this particular way where these double bonds are conjugated, those electrons can delocalize around that ring, right? And so if we have a fully conjugated ring, our electrons can go around and around that whole ring. That is our first rule that we need in order to be aromatic. We got to have a fully conjugated ring, all right? So how do we spy whether we have a fully conjugated ring? That means we have a ring of sp2 hybridized carbons. It's those p orbitals in my ring that are allowing those electrons to move, right? So that's how we make sure that we have this fully conjugated ring here. We're looking for a ring of sp2 hybridized, and actually not even carbons, sp2 hybridized atoms. Okay, and so why is that going to make our compound aromatic? Well, just like we saw before, when we have this fully conjugated ring, rather when we have conjugated double bonds, our electrons can delocalize around that ring. Okay, so benzene, we just kind of want to convince ourselves, is a fully conjugated ring. It's a ring of sp2 hybridized carbons, which means that these electrons are allowed to delocalize around that ring. So what do we think? This aromaticity, these delocalized electrons, is that going to make this molecule more stable or less stable? More stable, right? Just like before. And now it's kind of like conjugation on crack, right? Because it's not just in a line, but they can go around the entire ring here. So that's one of these main features we're going to see about aromatic molecules, is that they are very stable molecules. And that checks out just based on what we discussed last chapter, right? About these conjugated pi bonds. Our next rule here kind of comes out of left field, though. All right, not only do you have to be a fully conjugated ring, you also have to have an odd number of delocalized electron pairs. All right, and we'll actually won't get to it till the end of to the beginning of next class, but this is another important feature for these aromatic molecules. They have to have an odd number of delocalized electron pairs. It turns out if there's an even number of electron pairs, that's bad. All right, and again, it's kind of weird to see, and we'll explore this a little bit more next class period. For right now, you're just going to trust me. All right, these are the two features that we need our molecule to have in order to be classified as aromatic. Okay, so if we look at benzene real quick, let's just make sure that we can convince ourselves that indeed this molecule is aromatic. All right, so first we're going to make sure that all of our atoms in our ring are sp2 hybridized. Well, since these are on either side of that double bond, they're sp2 hybridized. All right, so again, to be clear, I'm coloring in these sp2 hybridized atoms in orange. These are also about a double bond, so they're sp2 hybridized. These are also about a double bond, so sp2 hybridized, right? So in terms of rule 1, check, check. We pass rule 1. All right, now we need an odd number of delocalized electron pairs. So this pi bond here will be delocalized because it's conjugated to this pi bond here, so that one will be delocalized, and this one here. So 1, 2, 3, indeed we have an odd number of delocalized electron pairs, right? So check, check. This is a compound that we would classify as aromatic. All right, let's look on to these two examples here. We're going to see whether or not they pass rule 1, being a fully conjugated ring, and rule 2, having that odd number of delocalized electron pairs. All right, so this one right here, what do we think? Do we have a fully conjugated ring? No, because we have these sp2 hybridized carbons. So we do have these conjugated pi bonds here, but it isn't a fully conjugated ring. Because when I get to this carbon right here, what's the hybridization of this one? This one is sp3 hybridized. So it does not have a p orbital that can accept those electrons. So although my electrons can delocalize back and forth, they cannot delocalize around that full ring. All right, so this molecule here fails rule 1, which means we don't even go on to rule 2. If you fail rule 1, you are considered a non-aromatic compound. All right, and then lastly, our cyclobutadiene here. Do we have a fully conjugated ring? Yeah. All right, so this carbon about my double bonds are sp2 hybridized. These carbons about that double bond are sp2 hybridized. So indeed, this entire ring is sp2 hybridized. So we got our fully conjugated ring. But how many delocalized electron pairs do we have? Two, right? This one here and this one here. And 1, 2 is not an odd number. So this one passes rule 1 but fails rule 2. This is a compound that we would classify as anti-aromatic. All right? Whereas aromatic compounds are super stable. Non-aromatic compounds are like meh stability. They're just kind of average. Nothing special, nothing detrimental. But these anti-aromatic compounds, these fully conjugated rings, but rings that have an even number of delocalized electrons, these are super unstable. Okay, so this is the name of the game for today. We're going to be classifying compounds as being either aromatic, non-aromatic, or anti-aromatic according to these two rules that we laid out here, right? Do we have a fully conjugated ring? Where was it? Do we have that fully conjugated ring, a ring of sp2 hybridized atoms? And importantly, this other weird rule about having an odd number of delocalized electron pairs. If you pass both of these rules, you're aromatic. If you fail rule 1, you're non-aromatic. But if you pass rule 1 and fail rule 2, then you're this weird category of anti-aromatic. Again, super unstable molecules. So this second rule here is kind of weird. And again, you're just going to trust me on this for today, and we'll explore why that is a little bit next lecture. But again, the name of the game here is to classify compounds into one of these three categories. Okay? Cool. So now we're going to move on to these examples here. I'm going to give you guys a few minutes to copy these structures down, as well as classify them into one of those three buckets: aromatic, non-aromatic, or anti-aromatic. let's go through these here. Let's look at this first one. All right, anybody got a guess? Category for this first one here. Aromatic, non-aromatic, or anti-aromatic? So this one is aromatic. Let's go through and convince ourselves. It's a little hard to see because we have what are called a fused ring structure. We got these two rings stuck together. But we're going to play the exact same game that we played before, where we see if we have this ring of sp2 hybridized atoms. All right, so importantly, these are sp2 about that double bond. These are sp2 about that double bond, and these are also about a double bond. So they're also sp2 hybridized, right? All four of those bonds are to carbon atoms, but they're still sp2 hybridized. And so over here as well, two sp2 hybridized atoms. Over here as well, two sp2 hybridized atoms. So we see we indeed have this ring structure, all of sp2 hybridized carbons, right? So a fully conjugated ring. So check, check, this does pass rule 1. So then we're going to go through and we're going to count how many delocalized electron pairs we have. Well, all three of these pi bonds will delocalize, as well as these two. That brings me up to a total of 1, 2, 3, 4, 5, which is indeed an odd number. All right, so we pass rule 1 and rule 2, which means that we have an aromatic compound here. All right, our little stop sign here. Aromatic, anti-aromatic, or non-aromatic. What do we think? So this would be anti-aromatic. Because if we look, we do have that fully conjugated ring, right? All sp2 hybridized. But when we go through and count, we have 1, 2, 3, 4 pairs of delocalized electrons. So it fails that second rule, right? We got an even number of delocalized electron pairs, making this that weird, super unstable anti-aromatic compound. All right, and then what about this third example here? All right, so this one would actually be non-aromatic, because even though all of my carbons are sp2 hybridized, remember, in order to be aromatic, we have to have a fully conjugated ring. That ring structure is essential for this concept of aromaticity. All right, the electrons can freely move around that ring. Okay, so this one just fails rule 1. We don't even go on to rule 2. We're just going to say, boom, fails rule 1, meaning this is a non-aromatic compound. All right, so now these next two examples have these carbocations. So how do we deal with carbocations? We're going to do the same two rules. All right, we're going to figure out whether we have this fully conjugated ring. If we look over here, we know that these are all sp2 hybridized carbons, right, because of those double bonds. But what about this carbocation here? All right, well, remember, like we said at the beginning of class when we did that example with our nitro group, we had this carbocation that formed at the end here because we spy these 1, 2, 3 bonds and no lone pairs. Remember, carbocations are kind of weird because they're carbons with incomplete octets. All right, so a carbocation is indeed sp2 hybridized. All right, so we're going to note carbocations are sp2 hybridized. So just like these other carbons over here, they're sharing a pair of electrons between those two p orbitals. That's that pi bond. Carbocations are also sp2 hybridized. They just have empty p orbitals. So our carbocation sp2 hybridized with an empty p orbital. that empty p orbital is able to accept electrons from these neighboring p orbitals. So indeed, these electrons can fully delocalize around that ring. All right, so when we're going through in rule 1 here, carbocations will not break the hybridization of our ring, or rather the conjugation of our ring, because they are themselves sp2 hybridized. All right, they got an empty p orbital that can accept electrons. But now when I go to count my, so check, pass rule 1. Now when I go to count my number of electron pairs, I got 1, 2. Does this carbocation have a pair of electrons? No. So although it doesn't break the conjugation of our ring, it also doesn't contribute to the total number of electrons at all. So in this case, this ring has only 1, 2 pairs of delocalized electrons. So does it pass or fail rule 2? It fails, right? 2 is an even number. So this would be an anti-aromatic compound. All right, so how do we deal with carbocations? Carbocations are sp2 hybridized. They will not ruin the conjugation of a ring, but they themselves are not contributing any electrons either. All right, so then everybody take a second. I know it's really fun to draw these 7-membered rings, all right? But do this second example over here, classifying as aromatic, non-aromatic, or anti-aromatic. What do we think? So this one will be aromatic, because again, I'm going to go through and highlight all my sp2 hybridized carbons, and I'm going to remember that carbocations are also sp2 hybridized, so I indeed have that fully conjugated ring. Check, check. All right, and now I got to go through and count my number of delocalized electron pairs. I have 1, 2, 3, and that carbocation does not contribute any electrons, so I got 3 delocalized pairs. Check, check, this compound would be aromatic. All right, so we got our neutral compound examples that we did. Now we know how to deal with positively charged carbocations. All right, the last one we're going to talk about are heterocyclic rings. A heterocyclic ring is a ring containing a heteroatom Does anybody know what I mean by heteroatom in organic chemistry? A heteroatom would be anything other than carbon and hydrogen. All right, so these are ring structures that contain other atoms. So for example, a nitrogen or an oxygen in that ring structure. All right, and the most important consequence of these heteroatoms is that these heteroatoms have lone pairs. All right, and that's going to be kind of the trick here that we're going to have to sort of apply for our rules, is thinking about what's going to happen to that lone pair of electrons. All right, so we have our same two rules for aromaticity here. All right, let's do this first one together here. Okay, I want to figure out whether I have this fully conjugated ring. All right, so I'm going to go through and highlight my sp2 hybridized atoms. Well, I know these 4 carbons right here are sp2 hybridized, but what about my nitrogen here? All right. So it turns out that these heteroatoms, this nitrogen, it gets to choose whether or not it's going to be sp2 or sp3 hybridized. It gets to choose whether it's going to put this lone pair of electrons in a p orbital where it can delocalize around this ring, or if it's going to keep it in an sp3 hybridized orbital where it's physically pointed away from the ring. Right? So these heteroatoms with their lone pairs get to choose. They get to choose whether or not to let this electrons play with the other ones in our ring structure here, or whether to keep them separated, physically pointed away from that ring in space. All right, so that's the important part here. Our heteroatoms get to choose their hybridization. All right, they're going to choose to be sp2 hybridized with that lone pair in a p orbital if it makes the compound aromatic. All right, so if putting this pair of electrons in a p orbital, allowing it to delocalize around that ring, if that's going to make that ring aromatic, the nitrogen's like, sure, I'll be sp2 hybridized. But if it's not, if it's going to make it so that there's an even number of electron pairs, then it's going to choose instead to be sp3 hybridized. All right, sp3 hybridized with that lone pair pointed away from the ring if that would make that compound anti-aromatic. All right, so let's look at our first example here. Okay, this nitrogen, I don't know what its hybridization is yet because I got to figure out whether that lone pair would make this ring aromatic or anti-aromatic. So I'm going to go through and count this delocalized pair, this delocalized pair. If I included this lone pair as well, would that make this ring aromatic or anti-aromatic? Aromatic. Now I would have an odd number of electron pairs. So nitrogen says, sure, I'll go ahead and be sp2 hybridized so that this lone pair right here can be delocalized around that ring, making that ring aromatic. All right. Nitrogen just has one lone pair to worry about. Oxygens have 2 lone pairs, all right? But importantly, the only way that this thing could hybridize itself would be to sp2 hybridize itself. So only one of those pairs of electrons can ever be involved in delocalization. The other one will always stay what we call localized. All right, so for oxygen here, we want to note only one lone pair can be delocalized. One of them will always remain localized. All right, so this one over here, may or may not participate in that conjugation of that ring if it makes it aromatic. The other one's got to stay localized, has to stay put just on that oxygen atom. It can never have both of them participating in that delocalization around that ring. All right, so in order to figure out whether this compound is going to be aromatic, anti-aromatic, or non-aromatic, we're going to play the same game. These are all sp2 hybridized carbons. I don't know what my oxygen is yet. It gets to choose, so I have to count electron pairs here. These are going to be involved in delocalization. If it includes this one up here, is that compound aromatic or anti-aromatic? Aromatic, so indeed it will sp2 hybridize. So I pass both rule 1 and rule 2. This compound is aromatic. All right, and then lastly, what about this compound here? All right, so let's go through and figure out whether this passes rule 1. We know we got these two sp2 hybridized carbons. All right, but now we get to our oxygen here, and we don't know what its hybridization is. So we got to start counting electron pairs. Well, this one would be delocalized. This one would be delocalized if it contributes to the ring. What about this one? No, can't have both of them, right? So one of them we know is off limits here. This one's definitely going to be localized. So if we look, if it lets that pair of electrons participate in that ring, that would give us an even number. All right, so is it going to be sp2 hybridized? No. It's just not going to let that pair of electrons join into that ring. It's going to be sp3 hybridized, so that both of these electrons are physically pointing away from that ring. And if this is sp3 hybridized, then do I have a fully conjugated ring? No, all right? So you're never going to get an anti-aromatic heterocyclic compound. That heteroatom will simply just not participate in the conjugation of the ring if it's going to make it anti-aromatic, right? So these heterocyclic atoms, or rather heterocyclic molecules, are either anti-aromatic or non-aromatic if they choose not to be sp2 hybridized, okay? So you'll never see an anti-aromatic heterocyclic compound, all right? So both of these are then just going to remain localized. Cool. All right, so just to kind of recap here. First of all, we kind of randomly threw in this discussion of this new functional group, this nitro group, this strong electron withdrawing group. We're going to see it come up a few times throughout these next two chapters. All right, when we name our nitro groups, they're treated as substituents in our nomenclature. They go out front of the name. All right, and then the majority of our discussion was around these two rules of aromaticity, right? A compound is aromatic if it's a fully conjugated ring and has an odd number of electron pairs. If it passes both of those rules, we call that compound aromatic, which we said was a super stable compound. If it fails that first rule, if we don't have a fully conjugated ring, we put that in the bucket of being non-aromatic. And if it passes rule 1 but fails rule 2, we put that as an anti-aromatic compound. And for right now, you're just trusting me that anti-aromatic compounds are super unstable, all right? But that's kind of all we did today, was lump these compounds into one of these three buckets based on those two rules, all right? We did talk about complications of having carbocations or heterocyclic atoms in our ring, applying those same two rules. Okay? And where we'll pick up with next time is sort of exploring why anti-aromatic compounds are so unstable. All right? So we'll finish this chapter off next Monday. Cool. Enjoy your weekend.